Hi guys, welcome back to our discussion on infinite series. So in this video, I'll talk about differentiation and integration of power series. So specifically, I'll teach you how to differentiate and integrate a power series. So let me start by discussing the properties of functions defined by power series. So if the function f of x is equal to the summation of a sub n times x minus c quantity raised to the n power, where n is from 0 to infinity, which is also the same as a sub 0 if n is 0, plus a sub 1 times x minus c if n is equal to 1, plus a sub 2 times x minus c quantity raised to the second power if n is 2, and so on and so forth, has a radius of convergence of r which is greater than 0 or positive. Then on the interval c minus r to c plus r, f is differentiable and therefore continuous. So moreover, the derivative and antiderivative of the function f are as follows. So number one, the first derivative of f of x, denoted by f prime of x, is equal to the summation of n times a sub n times x minus c quantity raised to n minus 1, where n is from 1 to infinity. So this is also the same thing as a sub 1 plus 2 times a sub 2 times x minus c plus 3 times a sub 3 times x minus c quantity raised to the second power, and so on and so forth. So as you can see, when differentiating this function, we apply the power formula. So bring down the exponent, then times a sub n times x minus c, and then reduce the exponent by 1. So you have raised to n minus 1. On the other hand, the integral of f of x dx is equal to the constant of integration c plus the summation of a sub n times x minus c quantity raised to n plus 1 all over n plus 1, where n is from 0 to infinity. And this is equal to capital C, which is the constant of integration, plus a sub 0 times x minus c plus a sub 1 times x minus c quantity raised to the second power all over 2, plus a sub 2 times x minus c raised to the third power or all over 3, plus and so on and so forth. So to integrate this, we should have our previous knowledge of integration. Here we apply the power formula by adding the exponent by 1 divided by the exponent plus 1. So you have here x minus c quantity raised to n plus 1 all over n plus 1. Okay, the radius of convergence of the series obtained by differentiating or integrating a power series is the same as that of the original power series. The interval of convergence, however, may differ as a result of the behavior at the endpoints. Okay, so as an example, consider the function f of x, which is equal to the summation of x to the n all over n, where n is from 1 to infinity. That if the value of n is equal to 1, then you have x. If n is 2, then you have x squared all over 2. If n is 3, then you have x cubed all over 3, plus and so on and so forth. So from this function, we are asked to find the interval of convergence for each of the following functions. So letter A, we need to find the integral of f of x dx, B, f of x, and C, f prime of x. So from the given problem, given that f of x is equal to the summation of x raised to n all over n, where n is from 1 to positive infinity. So we need to find the first derivative and also the integral of this function. Okay, by theorem 9.21, the integral of this function, which is denoted by this notation, so this is read as integral of f of x dx, is equal to x raised to, you add the exponent by 1, so you have x raised to n plus 1 all over n times n plus 1, where n is from 1 to positive infinity, plus the constant of integration. And then the first derivative of this function is by power formula. This is equal to the summation of n x raised to n minus 1 all over n, where n is from 1 to positive infinity. And because n is common, so you cancel this out. So therefore, the first derivative of the function denoted by f prime of x is the summation of x raised to n minus 1, where n is from 1 to positive infinity. Okay, for letter A, now we need to find whether the integral of the series f of x dx converge from -1 to positive 1. So to show that, we need to use the ratio test. And recall that in ratio test, we need to evaluate the limits of u sub n plus 1 all over u sub n. Where in this example, your u sub n is x raised to n plus 1 all over n times n plus 1. So, u sub n plus 1 is obtained by replacing all the n variable here by n plus 1. So, you have x raised to n plus 1 is n plus 2 all over. This is n plus 1. This is n plus 1 plus 1. So, n plus 2. Then, times. So, instead of division, I use multiplication. Then, we get the reciprocal of the n term. So, you have n times n plus 1 all over x raised to n plus 1. But x raised to n plus 2 can be written as x to the n times x squared. Similarly, with x raised to n plus 1, you can write this as x raised to n times x. So, you can cancel out x raised to n and x. So, we have x times n is n squared plus n times 1 is n all over the product of the denominator, which is n squared plus 3n plus 2. And then we can write this as absolute value of x times the limits of n squared plus n all over n squared plus 3n plus 2 as n approaches infinity. So we can factor this out because x does not contain any n variable. So the limits of the absolute value of x is still absolute value of x. And then we evaluate the limits of this quadratic function or quadratic expression. Recall that to evaluate the limits of this, you divide each of the term by n squared. So you get 1 plus 1 over n, and then all over 1 plus 3 over n plus 2 over n. And recall that if we to evaluate the limits, we replace all the n variable by infinity. So yung 1 over infinity is 0, 3 over infinity is also 0, plus 2 over infinity squared is also equal to 0. So therefore, we have the absolute value of x times the limits of 1 is 1. And to make the series converge, this should be less than 1. So this inequality statement, absolute value of x is less than 1, can be written as x is greater than -1 but less than 1, which indicates that this integral converge within this interval. But we have to check at each endpoint now whether the series converge at -1 and +1. So to do that, we replace all x variable from the series by -1 and +1 and then check whether the series converge. Okay, so by replacing x by -1, this can now be written as -1 raised to n plus 1 all over n times n plus 1, where n is from 1 to positive infinity. And at n equals 1, this is 1/2. If n is 2, then this is -1 over 2 times 3. So this is an alternating series. And we can also observe that the terms are decreasing. 1/2 is greater than 1 over 2 times 3. This is greater than 1 over 3 times 4. And the limits of the n term of this series is equal to 0. So this indicates that this alternating series converge. Converge at -1. Okay, similarly, if the value of x is equal to 1, then the integral of f of x dx, which is summation of 1 raised to n plus 1, this is your x, all over n times n plus 1, where n is from 1 to infinity. And the n term of this series is 1 over n squared plus n. So we have to find a series which is bigger than this and with resemblance to this n term. So from here, we can say that this n term, 1 over n squared, is greater than the n term of the given series. And because this is bigger, and the series with this corresponding n term, which is summation of 1 over n squared, is we know that this is a convergent p-series. So we can therefore conclude that this given series also converge, because if the bigger series converge, then so does the smaller series. And because the series converge at -1 and +1, so these are included in the interval of convergence, and the radius of convergence is equal to 1. Okay, so in summary, if the function f of x is a series defined as summation of a sub n x minus c quantity raised to the n power, where n is from 0 to infinity, has a radius of convergence r is greater than 0, and on the interval of convergence c minus r to c plus r, um, f is differentiable and therefore continuous. Moreover, the derivative of the and the antiderivatives of the function f are as follows. So number one, the first derivative is the summation of a sub n times x minus c quantity raised to n minus 1, where n is from 1 to positive infinity. And this is equal to a sub 1 plus 2a sub 2 times x minus c plus 3a sub 3 times x minus c quantity raised to the second power, and so on and so forth. And the integral of the series, denoted by integral of f of x dx, is equal to the constant of integration c plus the summation of a sub n times x minus c quantity raised to n plus 1 all over n plus 1, where n is from 0 to infinity.